Hi there, myself Madhav Jha. I welcome you to CodeChef and let's have a look at this question.
The problem is maximum smaller. The problem difficulty is easy and there are no prerequisites. Let's have a read at the problem. You are given an array A of size n. Now the score of a permutation of integers 1 to n is defined as following. If the element at ith index is equal to I for at least one of the values of I that goes from 1 to n, the score will be negative 1. Otherwise, the score is the number of indices such that the value of element at pi is less than equal to element at I. And we need to find out the maximum possible score of some permutation p, and we need to print a valid permutation for that. For the input format, we have t test cases, and for each test case, we have two lines. The first line contains the integer n, that is size of our array A, and the second line will contain n-spaced integers, that is a1, a2 till an. As for the output, for each test case, we simply have to output two lines. The first line will contain the maximum possible score, and the second line will contain the permutation that will have n elements. If multiple answers are possible, all will be accepted. So we can print any one valid permutation. As for the constraints, number of test cases will go from 1 to 10 raised to 4, value of n will go from 2 to 2 into 10 raised to 5, and the value of elements itself will go from 1 to n. Let's see some sample inputs. Let's go through the second sample input. For this, the size of the array A is 3, and the elements here is 3, 1, and 2. Now, when we are creating this permutation P, what we're seeing is at the ith index, we have the element Pi, and both of them are actually an index in our element array A. Now, the element at I has to be greater than or equal, has to be greater than or equal to than the element at P of I. So since both of these are array, we can assume that this one index is pointing at another index and the element, that is ai, that we have is greater than or equal to the element that this points to, that is a of P of I. So with this, let's consider this permutation of again 3, 1 and 2 itself. The indexes are 1, 2 and 3. Let's write them too. Now 1 points to the element 3 and 3 points to the element 2. So since 3 is greater than equal to 2, this gives us a score of 1. Let's go next. The element at 2 is 1 and the element at 1 is 3. Since this does not satisfy our condition, this gives us no score. And lastly, the element at 3 is greater than equal to element at 2, that is 1. So this gives us again one more score. So in total, we get the score of 2 with this permutation, and this is the max that we can get. Why this is the max? Let's find out in how we can approach the solution. So as we have seen, we have the index I, and at this I we have the element pi. This is when we are talking about a permutation. Both of these are indices and they all point to our array A. In a way, this index I points to this index P of I in such a way that the element at I is greater than equal to the element at Pi, right? So let's do something. Let's sort the array A, and we'll do this with the indices. It means that once this array is sorted, we'll sort this in descending order. That would mean that A of I is greater than A of I plus 1, ideally greater than equal to something like this, right? And with this, we'll have these indices. Now, let's assume I create a permutation P of something like this. The ith index will have the element I plus 1. With this, what will happen? We know that both of them are indices of our array A, and with this, the element at I, that is ai, should be greater than equal to the element at ai plus 1. and this is confirmed, right? Because this is how we have sorted, and we know that these elements are in decreasing order. So with this, what we can do is we can simply fill all the ranks, something like this, right? So with this, what we are doing is the index will point to an element that will always be greater than or equal to the element that is pointed by the element itself of the permutation, that is our pi. Now with this, what will happen? Till n minus 1, everything will be good. What will happen at n minus 1? At n minus 1, this is the smallest element here, right? This is the smallest element. There is no other element, right? So whatever thing that we want to point at doesn't exist. There is no smaller element to point at. So we'll have to point at something random. Let's say we point at the starting index. That is our 0th index. Now if we do this for the n minus 1, right? For n minus 1 indices, we can get the score, that is plus 1 we'll get. So the score would be n minus 1. And for the last index, that is nth index, we are simply pointing it to 0, right? N minus 1 we point to n, and for n we are simply pointing back to 0. This gives us a score of n minus 1. Now the question arises, can we ever score n? We have established that n minus 1 is always possible. We simply sort this in decreasing order, and we simply form a cyclic permutation of the indices, the sorted indices that we get. When is it possible to get a score of n? It will only be possible if the index I and the element at this index pi both are pointing to the same number. Imagine this. I have two same numbers, right? Now this index can point to this one, and this index can point to the first one. Something similar can be seen in the sample inputs, like here. 1 is pointing to 2 and 2 is pointing to 1, and this does holds the condition of being less than equal to. So what we can do is, all the elements that are equal, they can simply end up pointing to each other. Let's say we have three indices that point to each other, right? Sorry, three indices that have the same element. Let's say these are two. This could be I, this could be j, and this could be the k index. So 1 can point to I, can point to j can point to k, and at the end k will point to I. With this, all three will point to each other, and all three will hold the condition that the index points to a number, and the number that it points to, that would be j, that is less than equal to. It will hold for all of this, and it will be a valid answer. Now with this, what is happening is we are only pointing with the same numbers. So if at the end there is some lone other number, there is not much that we can do. So for this to succeed, we need to make sure that we don't have a unique number. All the elements have someone that they can point at. So for this, what we can do is, for each number, we can simply have an array of indices, right? If this is equal to 1, it means that the max answer that we can form is n minus 1, as we have done here. We can go cyclic, and at the end, for the nth element, it will simply point to the 0th element, and we'll be done with it. But in case we have duplicates, that is, there exist multiple copies of all the numbers, right? It means it is not unique, then our answer would be n score we can get. So what we'll do is, all the same numbers will simply point to each other, and with this, we'll get our solution. Let's see how we can implement the solution in C++. So for each test case, we call the function solve. In solve, we take the input of n, and then we take the input of our array. Now, while we are doing so, we'll also create a sorted index array. This will only contain the indices, that is 0 to n minus 1. And then finally, we have our resultant array. Along with this, we also have a vector of vectors. This will include for each number its indices. Now, with this, we can find whether there exists a unique element or not. So for any number in M, if the number of indices where this occurs is equal to 1, it means that we have a unique element, and the score that we can get is now n minus 1. We cannot get the score n. Now in case there is a unique element, what we'll do is, we'll sort the array in descending order, and since we only need the indices, what we are doing is, we are sorting the indices based on the actual array. We sort it in the descending order, then First index will point to the next and so on until n minus 1. The last index will point to the first index, and with this we'll get a score of n minus 1. Now in case that there is no unique element, then what we'll do is we'll go over each numbers, and since there are multiple copies, they will point to each other in a cyclic manner. At the end, we simply print the resultant array, that is our permutation. Since while calculating this, the index that we dealt with was 0 based, so finally we are adding 1 to all the indices to make it 1 based. So we print the score and the permutation, and as you can see, I've got an EC in my C++ implementation. Let's see how we can implement this in Python. Again, for each test case, we call the function solve. We take the input of n, then we take the input of our array. Once we have this, we create for each number what are the indices where they appear. Once we have that, we find whether we have a unique element or not. If we have a unique element, we sort the indexes in the descending order of the numbers. Then we create a permutation. If this is not the case and we don't have a unique element, then multiple copies of each number will point to each other. At the end, we print the score and our permutation. And as you can see, I've got an EC in my Python implementation as well. So I hope you understood the problem, the approach, and how we can implement the solution in both C++ and Python. Have a very good day, and I'll see you in the next video.